In this video, we're going to look at linear equations and problem solving. Basically, this section has word problems. And the thing with word problems that most people don't like is that they can be hard to read, hard to know what's being asked, hard to know what information is relevant and which information is not, things like that. But also, the real issue is that it takes practice to really get the hang of word problems. So the word problems I'm about to show you, once you've seen them, you should be able to do some similar word problems, maybe with the help of looking back at notes or things like that. But the problem is that I'm only showing you 4, and so there can be other word problems that you might have that you don't know how to do. So the biggest strategy there is to just try something, and there are a few tools that I'll talk about in this video of things that you can do in general with word problems, not just on these specific word problems. The first tip that I have for you is to visualize a problem, and by visualizing it, actually, it's best to draw it out. And so in this particular case, if you read through the problem, we've got a page of our school yearbook, and they tell us the dimensions of it. They tell us about the margin on the left and the space to the right where there will be text, and that in between the pictures we need space. And what they're asking us to find is how wide each picture can be if we want there to be 3 across the width of the page. Now, all of this is telling us things about the width. And so if we draw out a picture of what's happening, we've got a page, so a rectangle, and we know that it's 9.5 by 12. But then if we look at the rest of the problem, the 12 isn't really going to matter here. It doesn't matter what the length of the page is. We're concerned about the width of the pictures, and we're concerned about the margins on the left and the right side. We're not really concerned about the height. So that's an important thing to realize. So on the left is a 1/2 inch margin. So there's a little space over here on the left, which we won't use. That's a 1/2 inch. And then on the right side, there's a bigger area that's where in a yearbook you would see the names of people over here on the side. That's 3¼ inches. And so then the rest of this space is going to be for our pictures. And the only problem with that is that our pictures can't be right next to each other. They've got to be, a 1/4 inch in between. So we'll have our pictures spaced out. This is terrible looking. Pretend it's better than it actually is. But in between the pictures, we've got 1/4 inch. And so what matters here is that all of these things from left to right have to add up to this width that's already been set by whoever makes the yearbook or makes those decisions. So if we wanted to do this in algebraic way, if we want to set up an equation, all of this has to add up to be 9.5 inches. And the things that are making up those 9.5 inches are the margin on the left, which was a 1/2, the space on the right, the 1/4 in between the pictures, and then the pictures themselves. And so that's actually what we're trying to find, is how wide these pictures are. And so we're going to use a variable to show that. We want them all to be the same width. So they're all going to be the same number added together 3 times. And we're going to put a variable to help us with this. We're going to call this 3W, W for width. So just to recap that, we know the whole page has to be 9.5 inches wide. All these other numbers, the 1/2, the 3 1/4, and the 2 1/4 came from the things we knew about the setup. And then we had to add 3W to take into account how wide that we're trying to find how wide the picture should be. To solve this, we would add together all these numbers, and that can be tricky because, hey, they're fractions. But if we do the 1/2 and the 2 1/4 together, that's 1. And then 1 plus 3 1/4 is 4 1/4. So that's a pretty good start. 9.5 equals 4 1/4 plus 3W. Then this is a normal equation to solve. We would subtract both sides by 4 1/4. And 9.5 minus 4 1/4, start from right to left and say, can I actually do 1/2 minus 1/4? which you can, you get a fourth. And that's easier just to think about in your head, otherwise we'd have to use common denominators. 9 minus 4, you can subtract and get 5. If the 1/4 had been bigger than the 1/2, we would have had to borrow. So at some point it might have been easier just to change this to decimals, but fortunately the stuff worked out pretty well for us. We didn't have to yet. If 5 1/4 is the amount of space basically for the 3 pictures, then we need to divide that by 3 to figure out what each picture will then have. To do that, 5 1/4 divided by 3, that's not super easy to divide like in your head. In fact, I would say it's very difficult to divide in your head. What we want to do is change 5 1/4 to an improper fraction. 5 times 4 is 20, plus 1 is 21. So 5 1/4 is 21/4. When we divide by 3, since this is a fraction, what we really want to do is multiply by the reciprocal, which is 1/3. So 21 over 4 divided by 3 is like timesing by a third. And we can cancel the 21 and the 3, and we get 7/4. A couple things here. One is we need a label. 7/4 what? It's inches. Also, anytime we're doing word problems especially, if they wrote the numbers in a certain way, we want our answer to be written that way. Normally in math, starting with Algebra 1 and going up, we don't necessarily change to mixed numbers every single time we get an improper fraction. But in this case, because they started off with mixed numbers, we want to change 7/4 into 1 3/4. It's kind of like if math had a grammar to it, this would be like a grammar sort of thing. That it's nice of us to put it this way instead of the other way. So that's that problem. In this problem, our hint is that we have equal situations. And so if we can come up with a way to model two different things and they want us to decide when they will be equal, then we'll set our two things equal to each other and solve it. That'll make more sense once we start setting this up. So at the beginning of the year, 30 students were playing a game I thought that I made up called Flappy Penguin, which may or may not actually exist, and 10 students were playing Algebra Go, which I definitely made up. Each day, 3 students uninstall Flappy Penguin, while 2 students install Algebra Go. After how many days will the number of students playing each game be equal? So let's think about this. We've got 30 for Flappy Penguin starting out, and we've got 10 for Algebra Go. We're trying to figure out when they will be equal based on how quickly the students are either installing or uninstalling. So for Flappy Penguin, it says 3 students uninstall. So that means that there are 3 fewer students each day. So we're going to subtract 3 and then put a variable next to the 3 that represents days. So days could be D or T, T for time, but something like that to signify how much time has passed. And if you think about it, if you plug in 0 for D, you get 30, which we're saying it starts at 30. If you plug in 1, you get 27, which is how many there would be after the first day. So it should make sense that that expression works. For Algebra Go, 2 students are installing it each day. And so installation means that it's growing in popularity, as Algebra Go should grow in popularity. So we want to add 2D so that we can account for it going up by 2 each day. Then this is a pretty easy equation to solve. We want to move the variables so they're together, and we want to move the numbers so that they're together. So for instance, I could add 3D to both sides. And then I would subtract 10. I could have done those in the same step if I'd been more adventurous. And then I would divide by 5 on both sides to finish. So D equals 4, and then the label for that is days. One thing we can do to check, and this only really is a good idea because 4 is a fairly small number, is we could actually make ourselves a chart using how many days and how many there were on each day. So Flappy Penguin started at 30 and went down by 3 each day. And at this point we're checking, so I already know where I want to stop, where I'm hoping to stop. So 10, 12, 14, 16, 18. Since they both ended up being 18 on day 4, that's a sign that, hey, we did it right. Great job. So that is that problem. Our hint on this problem is that we may need to use the fact that distance equals rate times time. This is one of the formulas that is probably the most used on a daily basis by anyone, because if you know the speed you're going and you know the distance you're needing to go, you divide those and you figure out how much time it should take. And that's something that if you're not already driving, once you start driving, you may end up being very concerned with to make sure that you're getting places on time. In this particular case, we've got kind of a Lion King situation. We've got a gazelle that can run 73 feet per second and a cheetah. So the gazelle can run 73 feet per second for several minutes. So it can't run forever, but it's more of a long distance runner as opposed to the cheetah, which can run faster at 85 feet per second, but can only sustain its top speed for about 20 seconds before it gets tired and has to slow down. So knowing this, how far away from the cheetah does the gazelle need to stay for it to be safe? And so one way of thinking of it is if we just say how far the cheetah can get in those 20 seconds, so 85 times 20, which is 1,700 feet. We could say that the gazelle needs to stay 1,700 feet away, and technically that's true, but if we want a more precise number, because 1,700 feet is kind of far, and the gazelle doesn't have to just stand there. The gazelle can be running away from the cheetah during those 20 seconds. So we're going to take the 73 and multiply it by 20 as well. So that gives us 1460. So if these two animals were racing, for instance, after 20 seconds, this is where they would be. And so that kind of gives you an idea of then what kind of head start the gazelle would need. And to figure that out, we would subtract the two numbers, which gives us 240. There's also another way we could have worked this out. We could have said, what is 85 minus 73 to find the difference in their speeds, and then times that by 20. And that would have given us the same answer. So if you were thinking that, great job. But the idea is that these two things will interact with each other, and we have to basically figure out, we didn't really write an equation, we just wanted to figure out how do these affect each other. And it might have helped to draw a picture. It might not have. On this problem, again, we're talking about distance, rate, and time. I made up this problem, so don't judge it too harshly. We've got a turtle and a hare, kind of like in the old story, except that was a tortoise instead of a hare. But anyway, we've got these two animals who are good friends and decide to get together one day to hang out. The problem is they live 100 feet apart and the turtle is super slow. It goes 0.5 feet per second. The hare is faster and can travel 4 feet per second, which means that they won't meet directly in the middle. They'll probably meet closer to where the turtle is, but we want to figure out how long it's going to take them to meet. So in order for us to do that, we need to think about the rate of the turtle, which is 0.5 times the amount of time it will take. And we want to think about the rate of the hare, which is 4, and the amount of time it will take. Both of those two expressions tell us the distance that the turtle and the hare travel respectively. But what we want is to somehow figure out if they are apart, if the turtle is over on the left side and the hare is on the right side, how can we work that into our set of equations here. This is actually, they're trying to meet in the middle somewhere, and so there's going to be an equal sign somewhere in here. If they were starting at the same place, if they were both starting over on the left, this would be different, but since they're not, we want to choose one of these 2 points to be 0, and then work the rest of the problem in such a way that makes sense. So for instance, if we think about what we learned in pre-algebra with the coordinate plane, with graphing, let's make the left over here 0, which means that the hair, which is 100 feet away, will be at 100. Then we think about where to put those in our equations. We're definitely going to have to put it plus. We don't have to actually put plus 0, but the 0 has to do with the turtle. It's starting at 0. The 100 is where the hair is starting. The only other thing we have to think about is that they're not going the same direction. And so one of these, I need to put a negative to account for that. So since the turtle starts at 0 and is going right's the positive direction, he's getting closer to 100, so his distance is going to go up, so this should be positive 0.5t. But the hair is going to the left, which in graphing is our negative direction, and we know that we want it to be getting smaller than 100 as it moves towards the turtle. So we're going to put a negative right here. This is the equation that we would solve to work out this problem. So I'm going to add 4t to both sides. That's 0. We don't really need. I didn't line this up very well, so I have to be careful. It's 4.5t equals 100. Now, if I am in Algebra 1, I'm probably not supposed to use a calculator. I'm supposed to work this out. So what I would do is 4.5 divided into 100. To do that, we move the decimal for the 4.5, which makes us move the decimal here as well. And put the decimal up top. We say, how many times does 45 go into 10? None. How many times does it go into 100? Twice. And then we subtract 45 times 2, which is 90. And then 45 into 100, hey, that's the same thing, so it's going to be 2 again. And since everything else is going to be zeros, this is just going to keep repeating. So this is 22.2 repeating, or we could say that it's about 22 seconds, if we're saying about. If they told us what to round to, we would definitely want to round to that, but they didn't. So at about 22 seconds, if nothing else, they'll be super close. And I guess they don't actually want to be right on top of each other. That sounds like a mess for one of them. But that's how we work out that problem. So the things we did strategy-wise are we drew a picture. We set things equal to each other, which we actually did in this problem as well as the second problem. And then we used the idea that distance equals rate times time. So this is just a few examples of some word problems, but really it's all about practicing and being willing to try to do something, even if you're not sure that it's the right thing.